Hi again. So today we're going to do part 2 of energy diagrams. We're going to be labeling energy diagrams. You should have already learned all of the terms in the last video. What you might want today that I haven't asked for in the other videos is, in addition to your notebook and something to write with, you might also want something to label with color, whether that's a highlighter, colored pencils, markers. All of the diagrams are going to be color coded. All right, so here's an exothermic energy diagram. Take a second and copy the picture into your notebook. But let's start off with what is on our axes. So on our Y, we have potential energy. Sometimes this is labeled PE. Potential energy is normally measured in kilojoules, so sometimes you'll also see a parentheses kJ for kilojoules. Our x-axis down here is our reaction coordinate. This is a fancy way of saying time is passing while the reaction is occurring. The next important thing is actually the shape of the curve. So make sure that this side is clearly higher than this side in the diagram you drew in your notebook. But this relatively flat line is going to represent our reactants. So every reaction is starting with our reactants. We proceed through the reaction and end up with our products. A little more of what this diagram can tell us. So from this line where our reactants are labeled all the way to the bottom, this is H reactants, or the enthalpy of our reactants. Remember from the last video, enthalpy means a measure of the energy in our reactants. So initially for exothermic reactions, our reactants start with more energy than our products end up with. This is because energy has been lost during the reaction. Energy has exited, hence why our products is lower on this side. Over here, we can also measure the enthalpy of our products. Next, this line's a little misleading, but from the very top of the hump to our reactants is the activation energy, or EA. So activation energy is the amount of energy it takes to initially start our reaction. And again, that is from the reactants line to the very top of the hump in our diagram. We can also read this in the reverse. So from right to left, and if you go from the products line all the way to the top of the hump, this is the activation energy of the reverse reaction. So from products, this black line, all the way to the top of the hump. We can also label the activated complex. So if you remember back to our last video, as our reactants are changing over to our products, there is a second in between the reactant and the products when bonds are breaking from the reactants, reforming into products, and we get what's called the activated complex, our highest energy moment. Next, so this is a line that goes from the reactants, and this line is lining up with the products. And when you're looking at between the products and the reactants, you get delta H. Delta H, again, is the heat of the reaction, or the enthalpy of the reaction. Another way to write it is H products, this should have one T, minus H reactants. So again, delta H, or heat of reaction. Sometimes this gets moved around a little bit, but it's always between the reactants and products line. Our very last piece is what happens if we add a catalyst. So like we talked about in the last video, catalysts are going to lower the activation energy. So we end up making a new pathway. So here you can see activation energy would be lowered if we added a catalyst, and we get a new pathway. We're now going to do the same thing with an endothermic energy diagram. So again, take a moment to copy down the image as you see it right now. Leave yourself enough room to label. But again, we start with potential energy, PE, on the y-axis. On the bottom, we see time is written. Again, it could be written as reaction coordinate. Basically, we're talking about a reaction going to completion. Make note of the shape again. So here we have a curve where the low end is over here, big end is over here, or a higher end, I should say. Remember, endothermic means we gain energy. Energy is absorbed, so our products end up with more energy than our reactants started with. So again, we have reactants to start with, products to end with. We can label right here our heat of reactants, or again, enthalpy of reactants, how much energy our reactants start with. Enthalpy of our products, or the amount of energy our products end up with. Again, it's super important, our endothermic reaction, our products line is higher than our reactants line. Our activation energy going from the reactants to the very top of our diagram. So activation energy for our forward reaction. Our activation energy for the reverse reaction going from our products to the very top hump of the diagram. So this would be activation energy of the reverse reaction. So if we read it this way. At the very tippy top of the hump, we have our activated complex. Our highest energy state is right here. And again, it's that moment when our reactants bonds are breaking, our products, the bonds are forming, and we get an intermediate substance. If we add a catalyst, we end up making an alternative pathway that, again, is going to decrease our activation energy. And lastly, this diagram already had it written in, but between our reactants and our products, we have delta H, or heat of reaction, enthalpy of reaction. Again, you need to know all those terms for it, but delta H is our products minus our reactants, the difference between these two. Now we're going to do a few practice questions, so just follow along. Here we have a energy diagram. Again, potential energy in kilojoules, progress of reaction, reaction coordinate, time. All of those can be written on the bottom. But first question, is this endothermic or exothermic, and how do you know? This is an exothermic energy diagram, and the reason I know that is, again, exothermic means we lose energy, and here it shows that our products have lost energy compared to our reactants. Energy has been released in this reaction, hence it's exothermic. Our next practice question is determine the heat of reaction, delta H, for this reaction. Remember, delta H is H products minus H reactants. We are going to get a numerical answer for this. So again, delta H is products minus reactants. Our products have about 60 kilojoules, so H product would be 60 kilojoules. Our reactants, 120 kilojoules. 60 minus 120 is negative 60 kilojoules. And if you remember in our last video, we talked about the fact that delta H is always negative for exothermic reactions. We have a negative delta H. This is an exothermic reaction. On to our next question. Determine the activation energy, EA, for this reaction. So just a reminder, our activation energy is the amount of energy it takes to start the reaction. It goes from the very top of the curve to our reactants. So in my opinion, we're talking about 220 kilojoules, 120 kilojoules for our reactants. So if we take the activated complex, 220 minus 120, it's about 100 kilojoules of energy in order to activate this reaction. Our next question, how much energy is in our activated complex, or what is the energy of our activated complex? So you need to know the activated complex is at the very top of the hump, and the energy for that would be about 220 kilojoules. And here is our last practice question. What is the activation energy for the reverse reaction? So again, we can read this going forward and we can read it going backwards. Our reverse activation energy is going to be between our products line and the very top of our hump. So if we solve for that, activated complex minus H products is about 220 kilojoules minus 60 kilojoules, which is 160 kilojoules of energy required for the reverse reaction to occur. So these are just a few of the types of questions you can get. Normally, you're going to get questions about solving for delta H, or the activation energy of the forward reaction the most. So those are the two to pay the closest attention to. You should be able to label this diagram. It's important to know where all of these different labels go on the diagram. After you complete this video, you can also go and do the energy diagram practice questions. If you have any questions for me, let me know. Otherwise, have a good day.